Okay, I'm going to start the workshop now. So what we'll do, welcome to the first of the sessions. And Frank Martin, we're just waiting for Frank Martin, but I'm not quite sure if he's going to be able to dial in. So I'll give the introduction and overview to start with. So first of all, welcome. Thank you very much for attending. And as I said earlier, there's two more sessions. There's one tomorrow at the same time, which is on country use cases, and then there's one on Thursday, which is on climate. In this one here, we'll be talking about an overview of satellite sensors. We realize that people may not know a lot about satellite sensors. Obviously, some of you will be experts, but we need to give a good idea of what's been happening with those. And also, we'll then talk about the CCI biomass across Australia, a nice case study for there. And then above ground biomass estimation across tropical and subtropical Africa. Looking at carbon crops with Martin Brandt, for example, and then comparison evaluation of global to regional above ground biomass products. Uncertainty associated with our biomass estimation, and we'll have a discussion about 4:30, and then there'll be some Menti questions for you to actually to answer as well there. So, if Frank Martin does appear, could somebody let me know, and then I'll actually also let him also give an introduction as well.
I'll let you know.
Thank you very much. Okay, so I'm going to go into the first talk, which is onto that one. And this is to give a bit of an overview of satellite sensors, past, present, and future of relevance to biomass and biomass change assessment. So, Earth observation data. They've been a large amount of sensors have been, well, increasingly so, sensors have been launched, and there's from the 1990s through to 2022 onwards as well. They consist primarily of the radar, where there's different sensitivities of branches and trunks, and the composition of forests in general and vegetation. And then there's the optical sensors, and there's LiDAR that give you information on the three-dimensional structure. And as we've gone through over time, you can see that these sensors have evolved. Some are follow-ons, such as the Japanese Earth Resources satellite and the ALOS and ALOS-2 and so on. And there's new sensors being developed specifically for biomass estimation as well. In terms of the LiDAR, this is obviously the ISAT glass with Space One LiDAR, which gives information on the structure of vegetation, and that's been significantly improved, that capability, by the JEDI and the ISAT-2. And there's proposals for other sensors coming in, such as the MOLI. We shouldn't forget, though, that in situ data, there are there's the requirement for in situ data, existing databases, for airborne and ground remote sensing data, such as terrestrial laser scanning and airborne LiDAR and so on. And that's important for developing algorithms and so on. And because there's different types of biomes around the world, so tropical forests, we'll talk about this today, mangroves and so on. There are certain peculiarities where the algorithms have to be developed and through with different sensors. So what I'm going to do is give you a bit of an overview. So optical sensors, one of the workhorses is the Landsat missions. Obviously, they've been going since the 1970s, really. And then obviously that is a continuity mission that has gone on. And it's providing very detailed information on the Earth's surface over a long period of time. They are obviously that's continuing, and then we've got the Sentinel-2, for example, from the European Space Agency, and there's other sensors coming forward. These are sort of workhorses which don't directly relate to biomass, but they provide information which is very relevant to understanding biomass and biomass change. The very high resolution sensors such as Planet and Pleiades, for example, are also equally important because they also inform, particularly on the chain side of things, what's actually happening on the ground, and they can be used for looking at tree species, for example, and so on. So these are the main optical sensors, and I say that the main thing is they can go very high resolution, they're easy to interpret, and obviously they've got a long time series as well on that as well. Then radar, there's a number of radar sensors. We've got the Sentinel series. Sentinel-1 is the main workhorse. We've had Envisat in the past as well. And then there's the SMOS, which is soil moisture system, and then the Japanese L-band radar. And then the L-band radar is particularly sensitive to woody material and has played a key role in actually retrieving biomass. Tandem X and the shuttle radar topographic mission before that is actually providing interferometric radar, and they actually looking for the height of vegetation, and some structural information can be obtained from that. And then the LiDAR data, the key sensors in say are the ISAT, the ISAT-2 and the JEDI, and these are currently, well, the JEDI and the ISAT-2 are currently operating, the ISAT was before then, and they're very important for looking at the structural characteristics of vegetation, which was shown before. So this suite of sensors, either singly or in combination, is very useful for estimating biomass at the global level. And it's one of the key things about this user requirements workshop is trying to see, well, how useful are these sensors? Are they going to be used in the future as well? How can we best use them to track biomass over time? So an example is the L-band vegetation optical depth, which is achieved from SMOS, and you can see now that it's actually that's quite useful, very coarse resolution, but high temporal frequency, and it provides information on the vegetation water content, and there is a spatial correlation between L-band VOD and reference above ground biomass maps. It does not really saturate over densely vegetated areas, and you can start to look at changes in biomass going forward. The C-band radar, we have Sentinel-1 mosaics now for multiple years, and also we have ALOS and ALOS-2 pulsar, which was done by the Japanese Space Exploration Agency. And they have been using CCI biomass to produce global maps of biomass in tons per hectare for multiple years, and that's the part of phase 2 is to continue that as well. So we've got maps out for 2010, 17, 18, 20, and they're looking at other years also. So this combination of sensors are used, and Oliver Cardis will talk about these for producing the biomass maps globally. There's also interferometric radar, which is particularly useful for areas like for mangroves. So some of these algorithms are quite difficult over mangrove areas, which have different characteristics, such as they're flooded into tidal flooding and so on. And so there's they can be used to estimate height, and the shuttle radar and Tandem X give you good estimates of height, and that this can be related then to the biomass of forests. So using that in combination is a good alternative in some cases. The ISAT-2 glass it really informs the algorithms for biomass retrieval. It's used a lot in CCI biomass as well. It can be used to form structural classifications, so taking a combination of height and cover from the ISAT footprints. And also it can be used to look at relationships between canopy height and canopy density around the world, and that has also been used to inform the CCI biomass algorithm as well. So you can sort of get an idea now that different sensors, like the C-band's looking more at the upper parts of the vegetation, the leaves and so on, but the L-band is looking much more at the woody components, but then you've got structural information coming out from the ISAT. So the combination of sensors is really important for retrieval. The JEDI, again, that's been used. It doesn't go into the boreal areas, so it does above ground biomass density. The algorithm is calibrated to use a combination of forest inventory plots with airborne laser scanner data. And that's been developed by the University of Maryland Forest Service and the NASA Goddard Space Flight Center. And it's 1 kilometer resolution maps, for example. You can see how the JEDI can be used sort of effectively directly to do biomass as well, but it's not complete coverage. The ISAT-2, though, is another that's also launched at about the same time, and that's got boreal woody above ground biomass, and that's derived from the ISAT-2 LiDAR with search reflectance and the Copernicus DM. And that was developed through NASA's Arctic Boreal Vulnerability Experiment and the ISAT-2 SART-C projects. There's ground transit estimates of above ground biomass along the tracks, and there's also these gridded estimates of above ground biomass density and uncertainty. All of these products are associated with uncertainty. And the important thing is that that covers the boreal zone, which is missing with the JEDI. In terms of future Earth observation data, there's obviously it's a golden age really coming forward. So we've got the NISAR, which is primarily an L-band radar, And then we've got the Biomass mission, which is a P-band radar to be launched pretty soon. And then there's the MOLAI, spaceborne LiDAR from the Japanese Aerospace Exploration Agency. And then Tandem L from DLR, and again ALOS 4 as well from JAXA. So these sensors are going to provide different views of the forest and maybe allow you to retrieve much more information on the structure of how the biomass is distributed through the vertical and horizontal space. One of the key parts of biomass is very complicated. So if I can explain this, you've got closed forests all the way through to the really open savannas, and I think Peter Scarth will really show this very clearly as well. But then you've got mangroves and you've got plantations. So each of those obviously have very different configurations about the arrangement of the wood in that space and leaves, but also through the growth stages. So as the forest grows, each of these environments grow and then they degrade through logging, dieback, and deforestation and so on. So you have these factors really complicate the retrieval of biomass. But then we've got fire, phenology, snow cover, tidal areas, inundation. These also complicate things. So we need to have sensors that also help to understand that, and also things that cause changes in biomass, like the fire, what could be the sea level or temperature. So these are the things. There's other sensors which we haven't talked about, which could be useful here. And finally, also integrated frameworks. So one thing we've worked a lot with is the Food and Agriculture Land Cover Classification System, where it links in it classifies land cover, but includes canopy cover, canopy height, and leaf type, and so on. So using these different sensors over different periods of time, different resolutions, start to maybe bring this information into classification systems as well. So in summary, the user requirement, a thing to think about is in the discussion is, what is the role of past satellite sensors for establishing historical baselines of biomass? How far do we need to go back? And what are the benefits of integrating data acquired by these different sensors? Optical, radar, and LiDAR, or their combinations alone or together. And the differing modes. There's lots of modes happening, like ScanSAR, for example, as opposed to fine-tuned dual data. How can the uncertainties be addressed? And Ron will talk about that when using data from sensors, again, on their own or in combination. What are the future requirements of satellite sensors when proposed, if they're planned in preparation, or what do we want? What's missing from that selection? So that's important too. I also want to highlight what organizational frameworks are in place to support the use and development of satellite sensors and algorithms like the Committee on Earth Observing Satellites, and also what integrated frameworks, such as I explained with the FAO-LCCS, can be used or developed to support retrieval and understanding of biomass and biomass dynamics. So that gives you hopefully a bit of a flavor of what we've got, because I know there's varying levels of expertise in this. And what I'd like to do now is to pass on to the next speaker,